Hello everyone and welcome to another episode of Solving Advent of Code in Rust and try to learn Rust in between. I'm Roberto and we have
Luciano, hello.
thank you everyone for following along. If you never did Advent of Code is a code challenge that is published around a Christmas period every year. We are working toward the last year one. There are 24 challenges and you can find them on adventofcode.com. We are publishing all our code to a GitHub repository. This one. And we have a YouTube channel where you find all the recording published. You can find the link in the description of the channel. We are reviewing the first exercise, first days of Advent of Code of last year. We are at day 3. They are not incredibly complicated, the first one at least. So we are going through them, and we already have some pull requests against our repository to have them solved. So if Luciano want to share the screen with
Sure.
day 3.
Okay, so should I read it? Maybe we will summarize it a little bit. But yeah, we continue the story where we are in this submarine and we need to do things to basically keep going with the submarine.
And everything is breaking down and nothing works.
Pretty much. So basically this time there are some odd noises and the submarine is producing some diagnostic report. And this is our puzzle input, which is a list of binary numbers. If we decode them properly, they can tell you many useful things about the condition of the submarine. The first parameter to check is the power consumption. You need to use the binary numbers in the diagnostic report to generate 2 new binary numbers called the gamma rate and the epsilon rate. And the power consumption can then be found by multiplying the gamma rate by the epsilon rate. So pretty much we need to decode a sequence of binary numbers, figure out 2 values. We multiply those 2 values and we get the power consumption. Now, how do we decode this sequence of binary numbers? So each bit in the gamma rate can be determined by finding the most common bit in the corresponding position of all numbers in the diagnostic report. That pretty much means every column here in the list of digits. So given this example, go ahead.
No, sorry. We have to go by column. Yeah, exactly.
So given this example, if we consider only the first bit of each number, there are 5 zeros. So if we count here 1, 2, 3, 4, and 5, and 7 ones. So if you count 1, 2, 3, 4, 5, 6, 7. Since the most common bit is 1, the first bit of the gamma rate is 1. The most common second bit of the numbers in the diagnostic report is 0. So the second bit of the gamma rate is 0. So if we count here 0, 0, 0, 0, 0, 0, 0, there are more zeros than 1. So the second bit of the gamma rate is 0. So the most common value of the third, the fourth, and the fifth bits are 1, 1, and 0 respectively. So we can figure out what are the remaining 3 bits of the gamma rate. So basically, for every column, we take the most common digit, and that is the digit of the gamma rate in that position. Make sense?
Yeah.
Okay. Similarly, we calculate the epsilon rate, but this time, rather than taking the most common, we take the least common. So basically, the epsilon rate and the gamma rate, they have inverse digits in every position. And once we have the gamma rate and the epsilon rate, we need to multiply them, and this is our answer for the puzzle.
Yeah, our input is wider than the example, obviously.
We can check it. It's like thousands of numbers, and we have more digits. Rather than having 5 digits, I think it was, here we have 12. Right? Yeah, 12.
Yeah, 12 digits.
Okay, so do we want to jump into the solution?
Yeah, part one. So basically, we have to count the number of ones and zero in the first column and put down which one is more common, and doing that for all the bits, all the columns of this matrix of numbers.
Exactly. So because we know that our every number in our input is 12 digits, we are basically pre-allocating an array with 12 positions. And what we want to put there is basically for every position, we want to count how many ones there are. Because by doing that, basically we have an index that for every column can easily tell us if one is the most common number or not. Because we also know that there are 1,000 numbers. So if one is less than 500, then it means that zero is the most common.
Yeah.
If one is bigger than 500, then one is the most common digit. So with just one array with 12 items, we can index pretty much the count of all the digits in our entire input. That's the idea. And of course, we know that it's 1,000 because we looked at the input file, but here we have a counter that as we go through the lines, we'll keep track of how many lines we have in the input. So at the end of this function, lines count will be 1,000. Okay, so at this point, we take every single line as a string and we go through the digits. And to do that, we read the line as an iterator of characters, and then we map that iterator and we check. If it's 1, the current value is 1. If it's otherwise, we use 0. Now, this is not the most comprehensive input validation, but we know
but
the input is good. Like we are not accepting any arbitrary input. We just use the file. So this is good enough code for now. Okay, so now the next thing to do is basically we say for every
there in line 5, you create what? An iterator. So you will have a position value, position value, position value. And in line 6, you have an enumerate that will give you position value, and so on. And with these 4 in line 6, you populate the array that you have initialized in line 2.
Exactly, because here the trick is that because this n can be either 1 or 0,
yeah,
we are always incrementing. And when we find that 0, we are basically not counting.
Yeah,
we are
adding we are adding 0 that make no difference.
Exactly. So this might be a little bit tricky to read, but it works because at the end we are going to have the count. For every line, we are increasing by 1 every single column where we find a 1.
Yeah, a more readable way could have been to have if C is a 1, if N is a 1, sorry, number of digits of I plus equal 1. Sorry, there is no plus in the rest. Yeah.
And then we are also increasing the line count because at this point we counted, we saw an extra line. Now, at this point, we have everything we need to be able to calculate the gamma rate and the epsilon rate, because again, for every column, we know how many ones there are in that column. So we initialize gamma and epsilon as 0. And here we are going to be doing a little bit of bit shifting to effectively produce the numbers. Because at the end of the day, we know that we are trying to figure out the digits, binary digits for gamma rate and epsilon rate. And the rules were that for gamma, I think we need to take the most common digit. So if the most common digit is 1, in that position we use 1. If the most common digit is 0, in that position we use 0. And epsilon is the opposite. So basically,
it's the other way around.
Exactly. We take the least common digit for every position. So here what we do is for every number of ones in this array we are located at the beginning.
And watch out that in this array, the number at index 0 is the most significant bit of the number. And the number in position 11 is the LSB, the less significative bit of the number. So just watch out this, because we created this way, because obviously when you go through the parsing of a string, on the left you have the MSB, and on the right you have the LSB.
Yeah, so if that was not the case, we should have reversed the iterator,
exactly.
basically.
But we created it in an handy way, so
what we do is initially we shift anyway because we are considering a new digit. And then what we do is, if the number of ones is bigger than lines count divided by 2, so that basically means if 1 is the most significant, the most occurring digit in that column, then what we do, we increase gamma by 1.
So we put a bit to 1 in the first position of this number. But remember that in line 16, every time we loop, we move the bits through our number. So it will become in the future, if there are other loops, it will shift to the most significative position.
Now, the other one is that in the else case, so when there are more zeros than ones, that means that in epsilon, we need to accumulate 1.
Yeah.
So basically, we never deal with zeros, because zeros would have no effect here in this bit shifting operation. We only accumulate ones, and that's why we figure out when there are more ones than zeros, then we accumulate in gamma. Vice versa, we accumulate in epsilon.
Because because when you bit shift, the bit that is coming in is a 0 in this case. Because it's not rolling and there is no carry, and so
I don't know if we can visualize this in like the first loop. Let's say we have 0 for epsilon. Sorry, for epsilon and gamma. Or maybe let's just think about gamma for now, because it's probably the easiest. Let's assume that when we start, we do this byte shift. What it happens when it's 0? Nothing changes.
No, it stays 0.
Then the next thing is, if there are more ones than zeros, then we increase gamma by 1. So at that point, gamma becomes 1. Let's just say that we are in this branch.
It would have been the same to do an or equal 1, because we know that the first bit will always be a 0, because we just shifted. So we know that with 0 will always be a 0. So adding 1 or doing or 1 is the same. Even from the CPU point of view, I think is exactly the same. ALU, ALU operations. So
now in the next iteration, we have 1, but we do the bit shift. So basically, we do this 1 0, let's say.
Yeah.
Then let's say that we end up here again. We do 11 at this point. Well, not 11, 1 1.
Yeah, 1 1
in binary. So 1 0. So if we keep going this way, I'm still assuming that we have 11. We shift again, so there will be another 0.
Yeah.
And now again, we might decide to put either a 0 or a 1, depending on.
We can decide of putting a 1 or putting nothing, because you are not putting a 0. You are doing nothing. It's a no operation.
Now, of course, and we keep doing this for 12 times, so for every single column. Now, the interesting thing is that when you do bit shifting, you're basically you are still dealing with integers, so we're not really having like arrays of bits to deal with, but it's a number that gets increased correctly, as if you were moving the binary digits this way. So that's why at the end of this for loop, we have 2 usides numbers, because we declare them as usides, and we can simply multiply them, and that's basically the solution.
Yeah, I have 2 questions.
Yeah, go ahead, and then we'll run the tests.
One is line 18, you are doing line counts /2. Is Rust smart and doing that operation only once, or is doing that division for every loop? Because you are inside a loop.
That's a good question.
Okay, I know that is a loop of 12 loops, so it's not 1 million loops. It's 12 loops. We don't care, 12 divisions.
Yeah, it's like 12 divisions versus 1 division, so probably it's not going to affect much.
But is smart enough to just do that once, because the line counts is not changing. So
Honestly,
why?
I have no idea. It's something we could benchmark at the end.
Okay, then I had another question that I forgot. Perfect.
There are, by the way, other ways to see the generated assembly for Rust if you want to have fun, but I wouldn't be able to read the assembly. So
you have an M1 on your machine?
No, there is like a website we can use. We copy paste the code.
Okay, yeah, but it will generate an assembly for which platform? Intel?
You pick in the website.
Okay. Because I think I can read an Intel assembler, but if it's an ARM one or I raise my hands and say sorry. I can't.
I cannot read any of them, so.
No, come on. It's
okay,
easy.
so let's run the tests. Okay, this seems to work. There are no questions in the chat, so should we go to part 2?
Another question that I could have was, let me think if I can remember it. If we are allocating an array of 12, because we know that the width of our numbers in binary is 12. If that was not no from before, what was the best structure to use? A vector?
Probably a vector, yeah.
So you were just saying number of digits is a vec, and then when you were going to a new position, you were pushing or incrementing, depending if the vector was long enough or not. Okay.
Or I suppose if you have a higher boundary, for instance, you know it's not going to be bigger than, I don't know, 1024 characters, then you can allocate all of that, and then you keep like an index that tells you how many actually you found.
So you create an array of big enough, a big enough
like
array.
A buffer, yeah.
Yeah. And then you just keep track of what was the width, the maximum width that you reached, like you keep count of the number of lines that you have in total.
Exactly. Yeah.
Okay.
An alternative could have been to use const generics, but this is more in the case where you might want to work with this particular solution with different inputs, and different inputs might have different sizes. So you could make it a generic constant argument. And at that point, you might have different solutions that pass. Given the input that you want to use, you might pass, I don't know, 5, for instance, if we wanted to run one from the examples, or 12 if we wanted to run the actual input.
Okay. I think
maybe this is something we can try if you want. And create a test for the example we have in the README.
Well, let's go with part 2. We can do that later if you want. So let's read part 2.
It's something we used before, cost generics, in other exercises. So basically, it allows here to use, I don't know, a T or whatever.
Yeah, T, and then when you instantiate but then you need to make part 1. You need to create a struct.
No, you can just put the generic here.
You put the
generic. Can just say T const usides, I think is the syntax. Or maybe it's const T usides. Yes, and then at this point you can use ERT.
But when you call part 1, you have to tell,
you need to say that part 1, you basically need to say that this is 12.
And that is called a turbofish.
So this is still working. And of course, if we want to write a test for the data that we have in the example where we know the number of digits, I think it's 5 or 6, we can create an
Yeah.
input in line and pass 5, and everything should work as well.
Yeah, let's try to create. If we have time, I think, to create the test for the example.
So this is the advantage of const generics, that test
part 1 example part 1. Yeah.
Let's copy paste
the input from the README.
Exactly this one. So here we can do like this.
Multi-line.
There is a nicer way to do multi-line, but I can never remember, so we'll go with this one for now. And now this one is 5, and what is the expected result? This one. No, wait, this is
198. 198. That is the real.
Okay, so if we run this, it should work. Let's see. It does.
Yeah. Okay.
So basically, with this const generic, we can use different sizes of array.
Cool. And this is less expensive than allocating a vector, because a vector is not in the stack, but is in the heap, probably. And also is multiple memory allocation every time you add a cell.
Yeah, unless you pre-allocate the capacity of that.
But at that point, you know already the size, and we are back in this scenario.
Or you are still guessing, and you might allocate way more than you actually need.
Yeah. Depends if you need the performances, or if you need to memory constraint. Yeah, depends. Or flexibility against memory usage and speed.
Okay, let's go with part 2. I don't even remember part 2, so let's see. Okay, so now that we have the power consumption, we should verify the life support rating, which can be determined by multiplying the oxygen generator rating by the CO2 scrubber rating. So again, we need to figure out 2 values somehow from this input and then multiply them together. It's just probably different rules.
Yeah. The criteria depends on which type of rating value you want to find. Yes. To find the oxygen generator rating, determine the most common value,
0 or 1 in the current bit position, and keep only the numbers with that bit in that position. So if 0 and 1 are equally common, then keep values with a 1 in the position being considered. Okay, so you take the entire input.
Yeah. You see which one is more frequent in the first column. Let's say 1, for example.
And you remove all the lines with 0 in the first column.
Done.
Right?
Then you go to column 2, of the number that you have left.
Yes.
And you do the same.
Yeah, and eventually you will end up with just one number. I think that was the idea.
Instead, for the CO2, instead of keeping the most frequent,
you keep the least frequent, and if they are equally common, keep value
the
with
one
0.
with the 0. Okay, so very simple. One is the inverse of the other, but
let's see if there is an example.
Yeah, it is there. For example, to determine the oxygen with the previous 5 bits numbers, we start with 12 numbers. The more
let me just pull
1 bit
here the numbers. So
we have
basically
12 of them.
So for the first one, 1 is the most common, right? So basically you would remove this guy, this guy, this guy, and this guy. Actually, let's do an example, and then we'll revert these changes. So everything starting from 0, we remove it. Starting with 0.
Yeah. Right? And so we have only this. At this point, we have how many of them? 7, right? Yes.
We have
7.
1, 2, 3, 4, 5, 6, 7. Yes. And what is the most common in the second digit?
0.
1, 0, 0, 0, 1, 0, 0. So 0 appears 4 times. So it's the most common. That means that we need to keep only the ones with 0 in the second position. So we remove
And
this
we
one,
remove that one.
we remove this one, and we
the
remove
last
this one.
At this
We
point,
do
we
the
have
same
4.
thing for this one. 1 is the most common because there are 3 ones and 1 0. So we remove this one. Then we go with this column. Again, 1 is the most common, so we keep this one. And the last one is 0 and 1, but we know that when there is the same number, we need to keep 1 for this particular value. So this will be our, what is called oxygen rate.
Yeah, the oxygen rate. As there is only one number left, stop. The oxygen generator rating is 23.
Which will be this number here.
Yeah.
So
Because
this is... Yeah, this is pretty much the algorithm for one number, and the algorithm for the other number is the same, except you need to keep the least occurring, the numbers with the least occurring digit in that particular column.
And if there is a tie, you have to keep the 0 and not the 1.
Exactly. So this is the algorithm, and then at the end you will have 2 numbers, you multiply them, and that's the solution. Cool. How did we implement this? Now, this one might be interesting because I think I wanted to try some optimization. So there is a little bit more overhead that we could probably ignore for now and then maybe run some benchmarks at the end.
So there is an enumeration.
But I was thinking, exactly, rather than using 0 ones, to use this enum, because I thought that the compiler could optimize them better. I'm not sure if that's actually the case, so we'll test this maybe later if we have time. For now, just assume that this is like a 1 u size, sorry, a 0 u size and a 1 u size. It's literally the same thing. Okay, so what do we do? Now, here I'm creating a vector with capacity 1000 just because I know that the input is going to be 1000. And what we need to do is to basically, for every line...
that is a vector of array of 12 elements, right?
Good point. Yeah, that's a vector of array of 12 digits. Yeah.
12 digits. Again, here, if we want to then test for the README example, we have to declare the constant.
We could make it this 12 generic.
Yeah, later after we explain it, everything.
So that's where we're going to accumulate all the numbers in our input as array of digits. Then, of course, for every line, what we do is for every character in that line, if the current character is a 1, we use digit 1. Otherwise, we use digit 0. At this point...
you create the array?
We create the actual number and we populate it. So for every single element in digits, because this is just an iterator, so we are not consuming anything yet. Then we allocate 12 positions of digits, and then we start to consume the iterator. And for every item, we just insert in the given position there in the array. And finally, we push the current array in the vector.
Question here, you can't collect into arrays in Rust?
I think you can, but you need to use try into, because so what happens is that, of course, you might have more elements than the actual space that you allocated for the array. So in that case, when you call try into, you will get an error rather than success. So it's just a little bit more annoying that you need to deal with a result and then unwrap, because of course that accumulation might just fail because of different sizes. We could try that later.
Yeah.
Also, the other thing is that in the previous edition of Rust, when you wanted to use try into, it was an additional trait that you needed to import, still in the core library, but something that you needed to explicitly import in your file. I think with the latest edition of Rust has been added to the default prelude, I think it's called. So all the traits that you have automatically imported. So now we can actually use try into without, like it's going to be immediately available
to import the library. And but this one is going to fail too if the number has more than 12 digits, right? If the input is longer than 12, you are doing the 4 in line 52, for example, 13 digits, and when you try to do num of
yes,
12,
you do like an
it
overflow.
will, it will overflow. Okay, so
So maybe the try into is actually safer if you want, because it's forcing us to deal with the error. Like this is just gonna panic.
yeah, this is going to panic badly if the input changes. Okay.
Okay, so at this point, we have a vector that contains for every item an array of 12 digits. What do? We need to figure out. So this is just another representation of all our input, basically. And now we can use this representation to figure out the oxygen rate and the CO2 scrubber rate. And there are two separate pieces of code. So let's start with the first one. Let's just start with the oxygen rate. So what do? Basically, we create a vector of references to the array of digit. And what we do is we collect all the values there. So initially, we're going to have a vector of 1,000 references there.
Because we are not changing anything there. We are just removing from the vector, from this vector in line 58, we are removing or keeping something. So every time, so we filter, but at this point, we don't have to copy the numbers around.
Exactly. Or we don't have to change the numbers themselves.
Yeah, we don't have to change. We keep it. That I? What is that I in line 59?
What is that I? I don't remember. Oh, yeah, we use it too. It's like the column.
Ah, okay, cool.
Maybe not the most, I don't know, meaningful name.
Yeah, no,
Maybe
but
we could just call it current column or something like that. So now what do? While the oxygen candidates, so this thing, while it's bigger than 1, so while we have multiple selections available, we keep looping. And at every loop, we need to filter out some numbers. So the first thing we do is we count how many ones there are in the current column. And this is basically all this code. So what we do is we do an iterator. We filter only for the items that have a 1 in that particular column. And then we count.
Even if n is a reference to an array, you can still call n square bracket I without the referencing how many times? 3?
3 times, yeah.
Yeah, okay.
Because 1 is coming, it's initially a reference. Then we are iterating, so you get another reference, then you are filtering, so you get another
one.
reference.
Okay.
But Rust should be smart enough to figure that out. Like you don't have to do asterisk.
Yeah, exactly. Put 3 asterisks, 3 stars to the reference everything. Okay, cool.
Then we figure out, is this the most common digit? If the number of ones is bigger. Oh yeah, of course. Here now this is a little bit dynamic compared from like before we were just counting 12 divided by 2. What was it? Yeah, and here now we need to know
1,000 divided by 2, not 12. 1,000.
Sorry, you're right. 1,000 divided by 2. Here we don't know how many items are left, so we count how many items are left, and we remove the number of ones. And if this value is, if number of ones is bigger or equal than this value, then it means that we need to keep
the one with 1.
The 1. So the 1 will be the most common digit. Otherwise, it's 0. I don't know if I'm explaining this very well.
And why you didn't just say if a number of ones is greater than the oxygen candidate len/2?
Oxygen candidate len
/2.
I suppose that's the same thing, right?
Yeah, I'm just asking if there was a reason behind the.
No, I think I didn't realize. Maybe it's even more readable that way.
Readable, probably yes. I think divisions, at least in Intel architecture, are more expensive than subtraction. So Let's keep it
Also,
like
maybe
this.
that's a little bit more efficient, but I
Yeah.
just didn't realize, to be honest.
Yeah, but even if division by 2, to be honest, is just a bit shift. But well, okay, don't listen to me.
Okay, so at this point, we know what is the most common digit for the current column.
And
so
we have
we
to
can filter out our oxygen candidate, which, by the way, notice that it was mutable.
Yeah.
Right? So what do? Is we basically reassign the oxygen candidates to itself while applying a filter. So we iterate, we filter out to make sure that we keep only the ones that have the most common digit. We use cloned because at this point we are basically cloning the reference at this point.
Filter is giving you a reference to a reference, so you have to clone the reference. Okay.
Exactly. And then we collect.
Question here. For example, in the set, there are a method of the sets to discard or to keep values based on rule and that are modifying the set that you call them on.
I think there is like drain filter, something like that we saw before.
Yeah. On the vector, there is nothing like that.
We can check if there is. I think there might be, but maybe it was still like experimental feature.
Oh, I remember that when we tried to use that on the set, it was still a night build, something.
So there is drain and drain filter.
Okay, and the difference is?
I think this one might just do what we want. Let's see if it works. And let's comment this one out. What's the problem with it? Yeah, it's still unstable. So there is this functionality, okay. But as we saw in sets, this functionality is unstable here. Now, there are ways to enable it. Either we use Rust nightly, or maybe there are other ways to just enable this feature. But yeah, let's actually add a comment. Let's copy all of this. And let's say the following
is still unstable.
Will be okay, that was a good question. At this point, we have I plus 1, which allows us to move to the next column, and we keep going.
Cool.
Then, in theory, at the end of this loop, we will have in this oxygen candidates a vector, but this vector will contain only one element, which is the number we're looking for.
Then we do the same for the CO2 scrubber, but the other way around.
The other way around. So here we are checking with minus, pretty much, and we use 1 and 0. And then what do?
We convert the array to a number.
Exactly. Notice that I need to use 0 because this is an array. We know there is going to be only one number, one value in the vector, and we take out that value. And then we do the usual bit shifting dance to convert the sequence of bits.
Can this be done with a fold?
I suppose it could. So let's put it as a note.
Fold is the reduce of.
And similarly, we will do it for this one.
You wrote withy. I don't know if it's intentional or.
No, it's not.
Okay, it's not slang.
And then finally, we multiply the two values.
We multiply them together.
Right. So let's run the test. Cool.
Now we can put the parameter like in part 1 to try with the README.
Yes, let's do that first. So let's do the
12 of the 5. How is called? Constant notation.
Const usides. Const generics. Sorry.
Const generics. Okay.
Because it's a generic parameter, but for constants, not for types or for lifetime. Because in Rust you have generics are many things, are not just types as in Java or C++, but they can also be generic lifetime or generic constants.
So look all the 12 that you have around and replace
So that
them
will
with
be
T.
T. There more? Yes. And
There.
here as well. Cool. That should be it. And now, of course, the test will complain because it doesn't know. Let's see if this is still working.
Yeah, still compiling, still working.
We can do the example.
Can you put the string that is the same of the README in some kind of constant?
We can put it here, I think. Const example. I think we need to say static, or actually, I don't think we need to say that. But yeah, let's
see if it complains and it wants us to say static.
And now here we can remove this one and we can say example input. Should work. Okay, perfect. And now here in this one, we want to do 5 again. Example input. We don't need this one anymore. Now let's see what was the value in the README.
Where is it? Is 23 multiplied by, finally, to find the life support rate, multiplied also in 23 by 10, and you get 230.
Okay, so that's the value.
230.
And it seems to work. Perfect. Actually, to be fair, we could do the same even for input, because we are including it twice in the...
You include it at the test level, okay.
And now we can just say input,
capital input.
and here. There must be a shortcut in Visual Studio Code to capitalize.
Yeah, probably, but don't ask me.
Okay, so let's rerun everything just to be sure we didn't break anything. And now we can try to use fold. Here, right?
Yeah, if you want to try, because the other one is unstable, let's wait, don't care about it.
This is basically equal to oxygen candidates 0.
0, because we have to take the first one.
Either.
Because it's a vector, you have to it's an array. You can iterate over an array?
I think so. Either. Right? Yeah, and now fold. Perfect. Okay, that's what we want. So init value is going to be 0. And then the function is going to have a digit, right?
And the previous value.
And
it must give you the accumulator value and the new value.
What comes first? I never
don't ask me.
I think always the accumulator comes first.
Yeah, because these are the digit and the accumulator is a usize.
Okay, so what we can do is, how do we accumulate?
We bit shift the accumulator, we add to the accumulator the digit.
Accumulator is 1, right?
Can we modify it or not?
I think so.
But well, we can do everything in one line, to be honest. Is that one shifted by 1 bit plus remove the equal? Is that shifted 1 bit plus
D2?
And you remove the semicolon, because
and we remove this one as well.
Now he's complaining about okay, no, just I think it must work. No, it doesn't like it.
Oh, it needs a semicolon there.
Okay. Let's
So-
try to comment.
So let's see if we comment this one out, if everything is still working. Yeah, seems so. So we can leave fold there. Is it more readable?
In my opinion, yes, and also it's not creating a mutable variable that you have to remember what it is, then you go through.
Okay, so let's do the same even here.
Yeah, if you remove the need for mutable variable in a Rust program, I think it's always better. If you have just new variables and you don't modify them, it is less prone to bugs.
Yeah, I'm curious if we could. This is an overkill probably, but we could probably implement a trait that gets automatically applied to an array of digits.
To get the number.
You could just do dot as, I don't know.
Yeah, dot give me a usize.
Yeah. But let's not go there for now.
What is parse to change between types?
Parse is a special one that comes from the from string.
Okay, it's only for
trait,
strings.
I think.
Okay.
Yeah.
Okay, it's only for strings. If you have to just change the type, there will be something else. Probably. Is a Uzi like the gun?
I think people generally use as underscore.
No. I mean 107. The type.
Oh yeah,
Uzi.
it's fold. So we say the first one is 0. Then we have a function that
The
takes
function is the same.
Oh, that's an interesting one.
The
Can
function
we
is the
just
same.
store the function somehow as like a closure? Now let me copy paste this and make it
let's
work
copy and
first.
paste. That works.
And then let's see if we can avoid that. That duplication. So we delete all of this. Should still work. It does. So now let's try to figure out. What do we call it? Two usides.
Yeah, two usides
equal this function. Does it complain? Oh yeah, we need to define the types.
Yeah,
so
we need to define the type because
this will be usides.
Usides, and the other is a reference to a digit. Okay, now it's happier.
Now it's happy, but of course it says you're never using this one. So let's see if we can just pass here this. Seems happy. Here seems happy as well.
Yeah. At this point, we could define a type that is called digits with the constant of the number of digits that is wrapping the array, and there's a member that is this fold. So you just do digits dot the element 0 dot usize. You cast it basically, and you have the value. Okay.
Yeah, still works. Okay, that's cool. Was there anything else we wanted to try?
We said something, I don't remember what.
So there was this 1 and 0 that we were not sure in terms of benchmarks, whether it did make a difference or not.
If you have benchmarks, you can run the benchmarks now. We can replace 0 and 1 with 0 and 1s and see
We
if
do
there
have
is.
benchmark. Oh, that's why it's complaining now with the benchmark, because of course we need to say
12.
part 1, 12.
Yeah.
And part 2, 12. Okay, so let me do a commit first.
Yeah.
Give me a terminal. type.
Are you still using the new keyboard?
And still not used to it.
Probably it's time to change the keyboard at this point.
Maybe. Okay, so how do we split the code to avoid duplication? Do we just duplicate crazily?
But can't you just run the benchmarks now, change the code, and run them again?
That's also an option. Yeah, why not? So cd year 2021 exercise 3 cargo bench.
Remember to go in the right folder, otherwise.
I think I am in the right folder. It's just recompiling everything in
Release mode.
Yeah, release mode. I was saying production mode, but it's actually release.
It's called release. Oh, I remember that because yesterday I compiled the stuff for microcontrollers and they have released and debug. Just the only reason why I remembered about it.
Okay, now running the tests.
Funny enough, one day I wanted to run all of these on top of a microcontroller because Rust is also addressing them as a compile device.
I think you can, and I think this could be an interesting thing to do together, maybe in a stream, because you have this thing that you can even use controllers that don't have an IP, but just you can use just the stack. And the standard library is divided in core and standard. And if you use only core, which you need like an annotation that says no std by default, then at that point you're not going to use any functionality that requires allocation. So I never tried that, but I've seen people doing this, and pretty much the standard library is already structured in such a way that you can avoid all allocations.
Okay. No, well, is the Raspberry Pi P0, so the Pico zero, the small one, the Raspberry Pico, and it has, I think, more than enough memory to allocate something. Obviously, not a huge amount of memory. We are in the order of kilobytes, but for this advent of code, we stay inside the kilobytes of memory. It's not that we go crazy far away from it. So now it runs.
I don't know what is it comparing to. Maybe I had some old run.
No idea. But we care just about part 2.
Yeah. Okay, so now what we want to do is basically remove all the references to digit, right? And we are going to be using 1 and 0s instead.
Yeah.
So every time there is digit 1, I'm going to be putting a 1. Every time there is a digit 0, I'm going to be putting a 0.
And then we change some type.
Every time we have digit, we need to say usides. Oh, no. Only digit this way.
Which was the other one that he wanted to change?
I think he was doing it case insensitive.
Case insensitive, no, please don't destroy the world. And now 2usides is complaining why? Because you don't have to do 2usides to a usides.
Oh, no, we just have to do D, right?
D, yeah, because it's already a usides.
And that's it. Yeah, I don't see any other issue. Let's just run the test to make sure it's still working. It's green. Okay, so now if we run the benchmarks.
Part 1, it will be just noise if there is any change. Yeah, a little bit slower, but 1%, I don't care.
No change in performance. So we can remove all this complexity and keep it simple.
Yeah, because basically probably is doing the same internally.
Yeah, my idea was that I thought that enums would be packed better because you only have two options. Instead, with a usides, you have more numbers.
Award.
Actually, I don't know if it's changing it from usides to u8.
That depends a lot on the architecture of the CPU. I mean, CPU are optimized to read and write the word size, and the word size can be nowadays 64, but it
Yeah,
can
and
be
usides
32,
is
64, 128, depending on the CPU architecture. Forcing a U8, probably it will still read a word, so still read the 64 bits, and then just keeping the first 8. That could be slower than using a U size, using a U8, because probably depending on the CPU architecture, though. So if you want to play around, but you have to play with bigger numbers than 1000 lines of input to get this kind of difference, in my opinion, because
probably, yeah.
we are going
Okay.
truly in the micro code of the CPU architecture and optimizing there. Too deep for me.
Okay, at this point, I think we are just about 1 hour, so probably I will
Yeah, we
close it here
can
for today.
close it for today. So let's wrap it up. You can find the recording on YouTube. The link is on the Twitch in the About section. If you're watching this on YouTube, we do live streaming on Twitch every Monday, 5 p.m. UTC. Make sure to check the Twitch link in the YouTube description. Give us a follow and like, dislike. Oh, now you can do giving dislike because they don't count them anymore. So give us all the dislikes that you want. Feel free to leave us comments, PR. The code repository is here. Banner, please. Perfect. Everything is well accepted. We are trying to learn Rust, so don't expect our solution to be the cleanest, the most idiomatic one. If you know better ways, tell us. Thank you for all the chats. And we are going to write some. Are we going to rate somebody or not?
Yes, so if you want to look at another language that is a little bit competing with Rust, I think it's a little bit behind, but it's getting there, called Zig language. We are going to rate
Zig. Yeah.
somebody that is, I think, a core contributor of Zig. So maybe you
Cool.
can learn something interesting there. So with that, we'll see you next time. Bye.
Bye.